Pick up your coffee cup. Go ahead. Actually do it. Hold it in your hand. Feels solid, right? Completely still. Not moving at all. Just sitting there in your palm stable, fixed, motionless. You are wrong, completely, utterly wrong. That cup is vibrating, shaking, jiggling with such ferocious intensity that if you could actually see what was happening at the atomic level, it would look like absolute chaos. Every single atom in that cup is moving, bouncing, colliding with its neighbors millions of times per a second. And I am not talking about some subtle quantum wobble that doesn't really matter. I am talking about real, violent, continuous motion happening right now in your hand. This is heat. Not some mysterious fluid, not an invisible substance flowing from hot things to cold things. Heat is motion, random, chaotic, uncoordinated motion of atoms and molecules. That is it. That is the whole story. And once you really understand this, once you truly get it, you'll never look at the world the same way again. See, most people walk around with this vague idea that heat is a thing. Something that objects contain. You heat up water. The water has heat in it. You touch a hot stove. Heat flows into your hand. The language we use makes it sound like heat is a substance. Something that moves from place to place. Something that can be added or removed. And historically, people actually believed this. Back in the 1700s, scientists thought heat was literally a fluid called caloric. They thought hot objects contained more caloric, cold objects contained less. And when you brought them together, the caloric would flow from one to the other until they balanced out. It made perfect sense. It explained everything they could observe, and it was completely wrong. The truth is so much stranger and so much more beautiful. Heat isn't a thing at all. It is what we call the random kinetic energy of particles. Temperature is just a measure of how fast, on average, those particles are moving. That is it. When something is hot, its atoms are moving fast. When something is cold, its atoms are moving slowly. There is no heat fluid. There is no mysterious substance. Just motion. Think about what this means. Right now, as you are sitting there, every atom in your body is jiggling. The molecules in your skin, in your bones, in your blood, all of them are in constant, frantic motion. They're not going anywhere, not on average anyway. They're just vibrating back and forth, bouncing off each other, moving in completely random directions. And that motion, that jiggling, is what temperature is. When you touch something cold, what is actually happening? The fast-moving molecules in your hand are colliding with the slower moving molecules in the cold object. And when they collide, they transfer some of their motion to the slower particles. Your molecules slow down. The object's molecules speed up, and you feel that change as coldness. But nothing is actually flowing. No substance is moving from you to the object, just motion. Just energy being shared through collisions. Now, here is where it gets genuinely mind, bending the atoms in a solid object. Say that coffee cup you are holding. They're not free to move around. They're locked in place by the forces between them, by the electrical attraction and repulsion holding the material together. So they can't just fly off in random directions like the molecules in a gas, but they're still moving. They're vibrating in place, oscillating back and forth around their equilibrium positions. And they're doing this constantly, always, as long as the temperature is above absolute zero. Absolute zero. That is the temperature where all this motion stops, where the jiggling finally comes to an end. Minus 273.15 degrees Celsius. Minus 459.67 degrees Fahrenheit. We write it as 0 Kelvin. And here is the thing. You can never actually get there. You can get close, incredibly close. Scientists have cooled things down to within a billionth of a degree of absolute zero. But you can never quite reach it. There is always some motion left. Always some jiggling. The universe seems to forbid perfect stillness. But let's stay in the everyday world for now. Room temperature about 20 degrees Celsius, 68 Fahrenheit. At this temperature, the molecules in the air around you are moving at something like 500 meters per second. That is over 1,100 miles per h are faster than the speed of sound. And they're not moving in straight lines either. They're constantly colliding with each other, bouncing off in new directions, creating this chaotic dance of motion. Every second, A single air molecule collides with other molecules billions of times. Billions, and each collision changes its direction, changes its speed, sends it careening off in some new random direction. So the path of any individual molecule is this crazy zigzag pattern, completely unpredictable, completely chaotic. We call this Brownian motion, and it is happening right now in the air you are breathing. Now think about what this means for something like a puff of smoke. You light a match, you get a little cloud of smoke particles, and what happens? The smoke spreads out. It diffuses. It fills the room. Why? Because the air molecules are constantly bombarding those smoke particles from all sides, pushing them around randomly, and over time, that random pushing spreads the smoke out evenly. This is diffusion, not some mysterious tendency for things to spread out, just the statistical result of countless random collisions. The smoke particles are doing a random walk, and random walks. If you do them long enough, eventually explore all available space. That is why smells spread. That is why if you drop food coloring in water, it eventually colors the whole glass. Random atomic motion. And here is something beautiful. You can actually see this. In 1827, a botanist named Robert Brown was looking at pollen grains suspended in water under a microscope. And he noticed that tiny particles from the pollen were jiggling around, moving in these erratic, random paths. He couldn't explain it, he thought. Maybe the particles were alive somehow. They weren't. What he was seeing was the particles being bombarded by water molecules, being pushed around by the random thermal motion of the liquid itself. This was direct visual evidence of atoms. Not the atoms themselves. Those are too small to see, even with a good microscope. But the effect of atoms, the jiggling they cause, that is visible. You can watch it happen. You can see matter being restless. And this wasn't fully explained until Einstein came along in 1905 and worked out the mathematics of Brownian motion, showing that it matched perfectly with the atomic theory of matter. So everything is jiggling. Everything. The desk under your hand, the screen you are looking at, the air around you, all of it in constant motion. But here's the question that should be bothering you. If everything is moving so chaotically, why does anything seem stable at all? Why doesn't your coffee cup just fall apart from all that internal vibration? The answer is that the forces holding matter together are incredibly strong. Remember that electrical force we talked about before. The one that would lift the entire Earth if you had just a 1% charge imbalance. Those same forces are what hold your coffee cup together. The atoms are vibrating, yes, but they're held in place by electromagnetic bonds that are so strong that thermal vibration can't break them. Not at room temperature anyway. But turn up the heat and things change. Give those atoms more energy, make them jiggle faster and harder, and eventually they can overcome the forces holding them in place. This is melting. When a solid melts, you are not changing the atoms themselves. You are not altering the forces between them. You are just giving them enough kinetic energy that they can break free from their fixed positions and start sliding past each other. The orderly crystal structure breaks down into the more chaotic arrangement of a liquid. And if you keep heating, if you give the molecules even more energy, they can break free from the liquid entirely and fly off as a gas boiling. Evaporation, it is all just atoms getting enough thermal energy to overcome the attractive forces and escape. Same atoms, same forces, just more motion. Now, here is something that should absolutely blow your mind. Temperature is an average. When we say something is at 20 degrees Celsius, we're talking about the average kinetic energy of the molecules. But individual molecules, they're all over the place. Some are moving slow. There is a whole distribution of speeds. This is why evaporation happens even below the boiling point. You leave a glass of water out, it slowly disappears, even though the water never reaches 100 degrees Celsius. Why? Because even at room temperature, some molecules have enough energy to escape. Not most of them, just the ones at the high end of the speed distribution. Those fast-moving molecules can break free from the liquid surface and fly off into the air. And when they do, they take their high kinetic energy with them, which lowers the average energy of what is left behind. This is why evaporation cools things down. It is not magic. It is just statistics. The same thing explains why you can smell things. That perfume, that coffee, that fresh bread. You are smelling molecules that have evaporated from the source and made their way through the air to your nose. Those molecules are in constant, random motion, bouncing around, diffusing outward, and eventually some of them happen to drift into your nostrils, where your olfactory receptors can detect them. You are literally inhaling tiny pieces of whatever you are smelling. And taste, same principle. Molecules dissolving off food into your saliva, drifting to your taste receptors. Every sensation you have involving smell or taste is just molecules in random thermal motion finding their way to your sensory cells. The world is constantly shedding pieces of itself into the air and water around it, and we're constantly sampling that molecular chaos. Let's talk about something even weirder: entropy. This is one of those words everyone's heard, but almost nobody really understands. People say things like, entropy is disorder, or entropy always increases, and they sort of vaguely understand that things tend to get messier over time. But what is it really? Entropy is a measure of how many different microscopic arrangements could give you the same macroscopic state. That is a mouthful. So let me break it down. Imagine you have a box divided in half. On one side, you have 100 gas molecules. On the other side, nothing. That is a very specific, very organized state. There are relatively few ways to arrange those molecules to get all of them on one side. Now remove the divider. What happens? The molecules spread out. They fill the whole box, and this state, with molecules evenly distributed, can be achieved in an absolutely astronomical number of different arrangements. You could shuffle the individual molecules around in countless ways and still have roughly half on each side. So this spread out state has much higher entropy than the concentrated state. And here is the key insight. The molecules are moving randomly. They're bouncing around, colliding, changing positions constantly, and random motion explores all possible arrangements with equal probability. So if there are way more arrangements that look spread out than arrangements that look concentrated, the system will almost certainly evolve toward the spread out state. Not because there is some law forcing it to spread out, just because there are more ways to be spread out than concentrated. This is the second law of thermodynamics. Entropy tends to increase. And it is not really a law at all, not like the laws of motion or the law of gravity. It is a statistical observation. It is overwhelmingly probable that random motion will take you from low entropy states to high entropy states. Just because there are more high entropy states to find, think about what this means. Every time you see something getting messier, something spreading out, something mixing together, you are watching entropy increase. You are watching the statistical consequences of random atomic motion. Drop a sugar cube in coffee. It dissolves and spreads out. Not because sugar wants to dissolve, because there are vastly more ways for sugar molecules to be mixed throughout the liquid than concentrated in one spot. And this is why you can't unscramble an egg. Once you've mixed the yolk and white together, once you've broken all those cell walls and let the protein spread and denature, there is no going back. The number of possible arrangements of all those molecules is so vast that the probability of them randomly reassembling into an intact egg is effectively zero. Not literally impossible, just so improbable that it would never happen, even if you waited longer than the age of the universe. Now, let's connect this back to heat and temperature. When two objects at different temperatures touch, heat flows from hot to cold. Always, you never see the reverse happen spontaneously. Why not? Because heat flow is really just energy being transferred through molecular collisions, and those collisions tend to equalize the kinetic energy. Fast molecules collide with slow molecules, transferring some of their motion. And there are vastly more ways for the energy to be evenly distributed and concentrated in one object. This is why you can't build a perpetual motion machine, why you can't extract useful work from a system without putting energy in, why engines must waste some heat. It is all statistics. It is all entropy. The second law of thermodynamics isn't some arbitrary rule the universe follows. It is an inevitable consequence of the fact that things are made of atoms in random motion. Here is something that used to puzzle people. If you put an ice cube in warm water, the ice melts and the water cools down until everything reaches the same temperature. Fine, but think about the energy. The energy that was in the fast, moving warm water molecules is now distributed among all the molecules, ice and water both. The total energy hasn't changed, but now you can't use it to do anything useful anymore. You can't run an engine on lukewarm water. The energy is still there, but it has become useless. This is what entropy really represents, the spreading out of energy into forms that can't do work. In the warm water, the energy was concentrated, organized. You could have used that temperature difference to run a heat engine, to do something useful. But once everything reaches the same temperature, the energy is still there. It is just spread out so evenly, so democratically among all the molecules that you can't extract it anymore. It has become waste heat, and this is the fate of the universe itself. Stars are burning, releasing energy, creating temperature differences. And those differences are slowly being eroded by the remorseless increase of entropy. Eventually, in the far, far future, everything will reach the same temperature. The universe will achieve what is called heat death. Not because there is no energy left, but because all the energy is spread out so evenly that nothing can happen anymore. No temperature differences, no flow. Just lukewarm, nothing extending forever. But we're not there yet, not even close. And in the meantime, we have this incredible phenomenon where local decreases in entropy are possible if you pay for them with larger increases somewhere else. This is how life works. Your body is incredibly organized, incredibly low entropy. You maintain this organization by eating food, using the chemical energy to power all your biological processes. And in doing so, you generate heat. You generate waste. You increase the entropy of your surroundings by more than you decrease your own internal entropy. Life is a local fight against entropy powered by the sun, which is burning hydrogen and increasing the entropy of the universe as a whole. We're all surfing on a wave of increasing disorder, creating little pockets of temporary order before everything ultimately spreads out to equilibrium. Now, let's think about something practical. Why does metal feel colder than wood even when they're the same temperature? This confused people for a long time. Both objects are at room temperature. Both should feel the same. But metal feels much colder. Why? It is about thermal conductivity. Metal conducts heat very well. When you touch it, heat flows rapidly from your hand into the metal. Your skin cools down quickly and you feel cold. Wood is a poor conductor. When you touch wood, heat flows much more slowly from your hand. Your skin stays warmer and the wood feels warm. But both started at the same temperature. The difference is how quickly they can accept heat from you. And what determines thermal conductivity? The ease with which those jiggling atoms can pass their motion along. In metals, electrons can move freely, carrying energy quickly from one place to another. In wood, the atoms are more locked in place, and energy has to transfer more slowly through direct collisions. Same jiggling, different ability to spread that jiggling around. This is also why you can stick your hand in a 200-degree oven and be fine for a few seconds. But if you touch a metal pan at that temperature, you'll burn instantly. The air in the oven is moving fast, yes, but it is a gas. Low density, not many molecules hitting your hand per second. And air is a terrible conductor of heat. So even though the air molecules are very hot, they can't transfer heat to you very quickly. The metal pan, though, dense, good conductor, touches your